having programs that help develop logical thinking, it just gives them a stopping point. It says, okay, I'm starting to feel like in this moment, my emotions are starting to dominate my thinking. Let me just pause and start applying some logical practice. So let's look at this problem and let's just start breaking it down into smaller pieces.
Hello and welcome to the Impact Insiders podcast, the podcast that explores real-life examples of people and organizations that are making an impact. My name is Marseille Kirsten and I'm the operations manager at Relative. Today we are talking to Chris Habberton to discuss computational thinking skills and how the in.code project specifically aims to address the lack of computational thinking skills that are taught in schools. Computational thinking and coding are hot topics discussed in schools and educational centers these days all around the world. So to give you a little bit of background and to put it into simple terms, computational thinking is the skill that we use to solve problems. So whether that is mathematical problems that we are faced with in school, or whether that is everyday problems that we face as adults. So therefore, we can see that coding is so much more than just programming or creating algorithms. So before we get into the depth of computational thinking and why it is important, I just want to give you a little bit of background on what it is. So computational thinking consists of 5 elements. So the first thing you would do while using your computational thinking skills is decomposition. So that means to break the problem into smaller pieces. The second element is pattern recognition. So that's where you look for similarities. The third element is abstraction. So that is where you decide what is important and worth focusing on, and then ignoring what's not important. The fourth element is algorithm design. So creating a step-by-step instruction guide to solve the problem at hand. And the fifth is debugging, which means fixing errors in your algorithm. As part of the Atomics Foundation, the in.code project was created with the goal of granting all children, regardless of whether they can afford it or not, the opportunity to learn computational thinking skills from a very young age. With us today is Chris Habberton, computer science teacher in New Zealand and co-founder of in.code. So in.code is a curriculum designed to teach computational thinking skills to children between the ages of 4 and 8 in a screen-free way. But Chris will explain that in a while. So to give a little bit of insight into the kind of person that Chris is, he did his first 80-kilometer walk at the age of only 10 years old. That is very impressive, Chris. Please tell us a little bit more about that.
Yeah, Marseille, thank you for inviting me onto the podcast. So I was fortunate enough to go to a school that offered a number of opportunities to learn lessons outside of the classroom. And one of those opportunities was every year, the school would do an annual long walk. Mm-hmm. Every grade would walk a set certain distance, but the college students would have the challenge of walking 80 kilometers.
Sure.
I know. During that time, I had been doing sort of the practice walks up for that big long walk. Mm-hmm. And I felt confident that I could do this thing. So I woke up at 3 a.m. and off I went. It was a long walk.
Getting a 10-year-old to wake up at 3 and then getting them to walk 80 kilometers, that is very impressive.
Yeah, it was. And I learned some really big lessons along the way as well. I think the most meaningful lesson that I learned was when you set yourself a goal, sometimes it takes longer than expected, mm-hmm. but it's all just about perseverance and one taking the next step that needs to be taken. And eventually you'll get there. But along with that, I was fortunate enough that my dad decided he would walk with me the entire way. And wow. Just having that support and that person next to you to kind of keep motivating you when you're feeling a bit low really sort of goes a long way. And I've tried to apply that into most of what I've done over the years. I like to take on big challenges, but I've also realized in order to get it done, one, you need to make sure you have a good support group behind you. And two, you've just got to keep the ball rolling, even if it takes a little bit longer than you originally thought.
Sure. Yeah. I think with perseverance and support, we can get very far. I think that's a great life lesson to learn. And as you mentioned, you've taken that into your life. So that is great. Yeah, so that is Chris Habberton, and we are going to delve a little bit deeper into computational thinking, what it is, what is in.code, during the rest of the session. So Chris, first of all, in a nutshell, can you please tell us what is computational thinking? So in my introduction, I gave a brief overview, but just, what is computational thinking for us that don't know anything about it?
Cool. So computational thinking is really a problem-solving process that we apply when taking a real sort of world problem and we want to create a computational solution to that problem. That there are 5 key stages to computational thinking. But what it really is, in its essence, is the strategy behind logical thinking. I think that's kind of the best way to look at it. And it gives us sort of a step-by-step process on how we can think logically.
Yeah. I think that is so important, because I think a lot of the times people think that you can either think logically or you can't. You get some people that they struggle with these logical thinking processes and strategies, but I think it's so amazing that we can teach that to people at a young age.
Yeah, definitely. I think when we make a decision, there are a number of factors that tend to influence what we decide and on how we do things, or how to solve a particular problem. Emotions obviously play a big role. Some people will make decisions that have a lot of an emotional sort of force behind them. Whereas computational thinking it really just helps you take a step back and say, okay, well, when I look at this problem, how can I break it down into smaller pieces so that it doesn't look as big, doesn't look as scary. I can now sort of work at one chunk at a time, find a solution for that one piece before worrying about the next piece. And I can test that initial component or piece of my problem until I get it right, until I get it fixed. And then I can worry about the next step. So in short, I think that is the best way to kind of look at computational thinking practically. But to take a step back, I think a person might ask themselves, how does computational thinking or programming relate to sort of us, in the sense of, we're not all programmers. So, why should I develop computational thinking? And to answer that question, I think we've really got to understand that computing devices were developed and designed around processing information. And the model that they used to create a computational device was really the way that we process information. So before we can jump into computational thinking, we first need to just tackle the mystery behind technology and rather look at how all technology is the same, and it actually is just a reflection on the way that we process things. So computational devices process information, and that information cycle can be defined in 5 key stages. So there's input, the computer receives data, it processes the data, it then has output. So either it's a visible output or an audio output. If it needs to be stored, it can be stored for a longer period of time. And if there are other devices involved, communication can take place between those devices. So that's kind of how a computer processes information. But a good example that I like to use with some of my students that I teach is, take a task, for example, your parent asks you to go and buy a bottle of milk at the shop, it's a very simple task, but you actually take that instruction and you process a number of elements that allow that purchasing of milk to take place. So you'll quickly think, have I got enough money? What time of the day is it? How far away is the shop? And you kind of determine all these things before you can actually decide to go out and buy that milk. So just like a computer receives input, we also receive input. We receive it by listening or seeing instructions or information. Even our other senses, taste, smell, they all contribute as input. Our brain then processes those pieces of information that we've gathered through input, and then we deliver some kind of output. So either it will be going to the shop and buying the milk. It might even just be saying, well, I can't go right now, the shops are closed, I'll have to go tomorrow. In which case you would have to remember that instruction, you'll have to store it, and then communicate that back with the other people involved that that decision might influence. So
that's very interesting, comparing the computer to how we process information. And I think if we understand those similarities, we will understand the device better as well. I think sometimes, we feel overwhelmed with technology, but I think the way that you explained it now, if we understand that the machine processes the information in the same way that we do the same steps, I think that would make it a lot easier to understand the machine as well.
Yeah, exactly. And you'll also start to see similarities between different devices. So you might look at your TV and you compare it to a smartphone, an iPhone or an Android phone. You might kind of see them as two separate things, but they're actually not. They're the same thing. They just sort of put together slightly differently to perform a specific task or specific purpose. But they all receive input, process instructions, deliver output, and if need be, store. So yeah, all very sort of what seems to be mystical and magical and confusing, it really, when you kind of break it down, it isn't. It's just the way that we process information, computers process it the same way.
Yeah, that's very interesting. And I think some of your students, when they don't listen to the instructions, I think it's just that process of, receiving the input and giving the output, that something went wrong in that process.
Yeah.
But that makes a lot of sense, Chris. Thanks for explaining that to us. And now I want to know, so now that we know what computational thinking skills are, now I want to know, why are these skills important to us? Why do we need to know them? Why do we need to learn these skills? Why do we need to have these skills?
Yeah, so I think there are a number of reasons why computational thinking is needed and why we should be focusing on instilling them and growing them and developing them in our youth. The most sort of industry-based concern that we have at the moment is we have limited amount of people that are entering the industry as developers or engineers or whatever it might be. And there are a couple of reasons why that is the case. The first is, at school level, computer science or information technology, depending on which country you're in, isn't readily accessible. So either students haven't had access to it in their primary education, and then when they enter senior or high school, they feel they don't have, or they won't have the ability to cope with the subject because it's a lot of new information. So, just normalizing things like programming, that programming isn't this superpower that only some people are able to utilize. But actually, everybody can learn it. It's just maybe we need to make that learning timeline a bit longer and start introducing it a bit younger, and in a way where younger students can relate to it and it doesn't appear to be too challenging or confusing or intimidating.
So Chris, would you say that it is it is better to learn it at a young age, or would you say, is it possible to learn these skills at a later stage in life? What are your thoughts on the timeline of when these skills should be taught?
So the skill of programming, I think, for me, not everybody wants to be a programmer, and that's okay. It is an industry where you've got to have a certain passion. You might even fit a certain type of profile that suits that type of industry and that type of job. So I don't expect everybody to be a programmer. And I think, that's where just getting students exposed to it is a win. They can then decide if it is something they want to do or if it isn't something they want to do. So, I think in terms of programming itself, primary school, introducing it at primary school, but really having more of a focus on the programming at sort of senior primary or intermediate phase learning would be a good thing to do. But I don't think computational thinking has to be seen as programming. Computational thinking is the way in which we can solve problems logically, and that can happen at a much younger age. From 4 years old. Bringing it into context that they can understand and engage with, and making the code more tangible, that they see as something that they use regularly, like, for example, puzzle pieces, rather than a computer screen and a keyboard and a mouse.
How do we use these skills as adults in life? So for kids, it's, the puzzle piece, but for adults, how do we use those skills in our everyday lives?
I think there are two sides to it. There's the logical thinking component, and then there's the actual programming skill. I think in terms of understanding programming, every industry nowadays has technology integrated into it. And in that technology, there's software. So by understanding software and how software works, you can get an understanding of what potential there is to create something that would be a solution within the industry you work in. You might not have developed your skills to the point where you can make that solution, but you understand the realm of what programming is and the possibilities that are available when developing solutions. So there's the programming side. I think that's that explained. But on the thinking side, some situations just require logical thinking. Like, you get put into a situation, like now, here's a good example. So living in New Zealand, there's a very strong focus on teenage anxiety and the negative effects that anxiety is having on our youth. And
I think that's a problem everywhere.
Yeah, it is. And it's because, people aren't sheltered from information as much as they were. Nowadays, teenagers have access to anything and everything in their hand. They can find out great tragedies as well as amazing projects. But most often than not, it leans towards the negative rather than the positive. And their brains are still developing, up until they're 25, 29, their brains are still developing. So a lot of their thinking is embedded in parts of their brain where logical thinking hasn't fully developed. So when they're making decisions, there's strong emotional influence in the way that they're processing what they're reading and what they're seeing. And then, they don't know how to process that information correctly. And so they internalize it, and then they get that fear and that anxiety of what it could mean for them. So, by having programs that help develop logical thinking, it just gives them a stopping point. It says, okay, I'm starting to feel like in this moment, my emotions are starting to dominate my thinking. Let me just pause and start applying some logical practice. So let's look at this problem and let's just start breaking it down into smaller pieces. How does this thing really affect me in my own space, or is it outside of my realm? And then once they start getting into using those skills, it might not be like an unconscious skill that they can just apply without even putting any thought to it. For some people, it really is a case of stopping and saying, okay, I'm going to tackle this problem logically rather than emotionally. But over time and practice, it does become just a way of thinking and a way in which you approach things.
Yeah, and then those steps of breaking it down, looking at what is important, step-by-step instruction guide, then looking at those different steps becomes sort of natural because, it's embedded in the way that you think.
Yes. And you also, part of a computational thinking is saying, we're not going to get this right the first time. One of our steps is to just test to see if it works. And if it doesn't work, re-evaluating it and saying, okay, well, what could I do differently to get a different outcome that possibly could work? So, it's not that built-in, if I don't get this right, I fail. Failing is just a part of the computational thinking process, and it's a part of the learning process. And, that on its own is a major benefit in this day and age.
Yeah, and I can definitely see where perseverance comes in. So that's where you need to persevere, try again, try and solve this problem. Very, very valuable skill. And I think that I can see how that can go hand in hand with learning these computational thinking skills.
Yeah, exactly.
That's incredibly interesting, Chris. And now I want to know, so you identified the problem of computational thinking skills and how it's taught in schools, and you co-founded the in.code project. And I gave a brief introduction to that. So, I want to know, how does in.code address this computational thinking, the computational thinking needs that we discussed?
Cool. So in.code is a project that focused on computational thinking at an early learning age. So from 4 years old until around 7 years old. And what we did was we said, okay, we want to provide activities that allow students to go through this computational thinking process. And we took some influence from different things. We enjoyed the storytelling of Dora the Explorer. So like there's a little bit of that sort of spice thrown into the mix. But we also wanted it to be relevant to what they're doing in the classroom at that moment in time. So we took the curriculum, the South African curriculum, and the themes that are within the curriculum, and we started kind of blowing those themes out and creating problems that can be solved computationally while still discussing those themes.
So Chris, does that mean that, this in.code curriculum is not something separate, but that it is sort of part of your everyday teaching experience?
Exactly. It's just it's a part of what you would be doing as a preschool teacher or an early learning teacher as your normal day-to-day tasks. Mm-hmm. We've incorporated storytelling, so it might involve reading a story, then asking some questions, so memory recall through auditory comprehension, and then we've taken those sort of normal learning practices, and then toward the end of the lesson, we've brought in a computational problem that they solve by giving a sort of sequenced set of instructions that need to meet a required outcome.
Sure, that is very interesting. And I want to know, you specifically said that it's based on the South African curriculum, but can this be applied in other curriculums across the world as well?
Yes, it can be. I mean, we say South African curriculum, but we cover the same topics that all early learning institutions will deliver. So, we focus on fine motor skills. We focus on tackling or creating content around subject matter like health and well-being. We look at numeracy and literacy. So all your core learning areas, we just might have additional themes brought in, like, for example, dinosaurs, or learning the weather, or the days of the week, or, it's that sort of content that becomes a part of our lessons.
That's very interesting. And as you mentioned, it's on the specific early learning ages 4 to 7 category. And as you mentioned, also those are very important. It's a very important time for kids to learn these skills. So it's great that it can be incorporated in their everyday life, in their school, and it's not something that needs to be separate.
Yeah, exactly. And we've tried to make it accessible in the sense that not everybody wants their preschooler to be on a computing device. So we've kept everything sort of unplugged, in the sense that it's all screenless activities. We source and develop learning tools that allow you to program, but it is physical and tangible code rather than sort of screen-based programming code, which is really, really good.
That's amazing. So Chris, while you've been involved with this in.code project, what surprising hurdles have you come across?
So we started this project in 2016, and probably one of the bigger hurdles that we had to come across was, one, the fear of it being programming. Preschool teachers are nervous about learning something that they feel that is quite a specialized field, and there's also the price point. Schools generally have very strict budgets, and being able to buy the resources that are needed, generally, schools are nervous to commit to those sort of costs. They tend to lean to a extramural activity model, but that doesn't make it accessible to everyone. That only makes it accessible to the students that can afford it. And we want to pioneer a path so that our curriculum and our learning can be beneficial to everyone in the classroom, not just those who can afford it.
Oh, that's great to hear, Chris. And that is the end of our discussion. Thank you very much to Chris Habberton for this fascinating and informative discussion on computational thinking skills and on the in.code project. I think it's definitely something to think about and to do more research about. This has been an Impact Insiders podcast powered by Relative Impact. Subscribe to our podcast to make sure you don't miss any of our future episodes. And for more information about Relative Impact and the work that we're doing, check out our website and sign up to our newsletter to get updates directly to your inbox.